SSL session keys in under 5 minutes. And as I just wrote that, I realized that's pretty funny, because if it took 5 minutes to establish session keys for SSL, we would never wait that long for the website to come up. In the world of SSL, we are going to have a symmetrical encryption algorithm between us and the web server using an encryption algorithm like RC4. To use a symmetrical encryption algorithm, we need to have symmetric keys, the same key on both sides to encrypt and decrypt the data. Well, how do we get those keys? That's what this MicroNugget is all about. Let's jump in. So my objective in less than 5 minutes is to explain how SSL operates. So wish me luck. Here we go. The client wants to initiate an SSL session with the server. So client here, acme.com here. Acme is only used as an example. So we have our three-way handshake that happens with TCP. That's all good. That's the birth of a brand new TCP session. Then the client sends a list of all these ciphers it's willing to do. What's a cipher, Keith? Well, a cipher such as what encryption algorithm am I going to use? What hashing algorithm? So it sends over a list, maybe like 11 to 20 different options in what it's willing and capable of doing. The server gets that list and says, great, I know what you're willing to do. Here's what I think we should do. It also sends over its digital certificate. This digital certificate of acme.com has several details in it, but the major one I'd like to focus on is something called the public key of acme.com. So the client receives the certificate of acme.com and now has the public key, I'll put that in green, has the public key of Acme. Now, what do you do with the public key? Well, let me explain how public and private key pairs operate. A long time before this conversation ever started, acme.com created a public-private key pair. And public and private key pairs are amazing. Whatever we encrypt with the public key can only be decrypted by the private key, and vice versa. So the acme.com keeps the private key private, and they advertise and they ship off their public key every day in digital certificates. And here's why. If the client has Acme's public key, the client can take data, encrypt it with the public key from acme.com, ship it over to acme.com, and only acme.com will be able to decrypt it. Well, that's handy, but what about traffic in the other direction? We need to encrypt that too. So to solve the actual session encryption that needs to happen both directions, we need to use a symmetrical encryption algorithm, such as RC4. Unfortunately, symmetrical algorithms require a key, and that key has to be known by both parties. So we have data that's going to be encrypted by RC4, and we have to have the same key on both sides. So here's how the public key comes into play. This client will generate a session key. It says, for example, as a key, let's use 123. That's a very small example of a session key. But if it wanted to use that, how do we get that session key over to acme.com without the internet eavesdropping and listening to what that key is? Because the key has to be secret. Well, what we do is the client takes Acme's public key and uses it to encrypt the session key and ships it back over. That's what's happening right over here. In fact, this line right there. When Acme gets it, it can decrypt the session key that was just sent using its private key, and now just the client and Acme both know the session key to use. They both can change from plain text, go to encryption mode using ciphers, and now we have an encrypted session. And that's, my friends, is a fairly high-level overview of how SSL can effectively set up shared keying material on both sides instantaneously and on demand. If you'd like more information on this, come and visit me in our CCNA security class, where we'll take a look at how the public key infrastructure works, which allows the client to verify that Acme certificate was valid in the first place. I hope this has been informative for you, and I'd like to thank you for viewing.